feedback? Who's looked at the lab? Okay, most of you. Is anybody finished? A couple of you. Okay, talk to me about the video. Is it helpful? Good? Lots of nodding? Okay, good. So the plan is, so the TAs are wrapping up lab 3 specs. They're being finalized right now, and they're wondering if they should do another video. It's going to be shorter than the first one. So it sounds like I saw lots of nodding, so I think we'll go ahead with it. Go ahead.
But maybe a little bit more detail in like text form.
You mean in the spec
there's
itself?
a lot of information. This is an hour, right, of stuff. And you know, not all of it is like central to what we're learning. And if I want to go back and reference something, it's maybe a little bit harder to go through like an hour video rather than having maybe like, because the lab, you know, it was like kind of some supplementary to the video rather than like the video being supplementary to the lab.
Right, that was by design. Okay.
And we could keep trying that, but I thought, maybe it's because I'm not used to it, that I thought it was a little
Good point that it's not searchable. We actually wanted to be very careful. What we don't want you to do for this lab is just cut and paste. So that's that's why we didn't want to. Essentially, we didn't want to put the text anywhere where you could get at it.
Okay. Well, maybe not the code, but like a description of that will. There was kind of like a high-level overview. It's like this, and then it might be this, but look to the video to actually get what's going on.
Right.
So,
Okay, well, hey, like I said, this is kind of an experimental format for us, so please just keep feedback coming, let us know how we can improve it. So let's go here and here.
I really liked the video as far as being able to, not be able to just cut and paste, but have to kind of think through it. One thing that would be really nice though is, I find as I'm going through the video, I can't just remember what each step is doing, so I'll have to like comment, like, oh, this is doing this, or this is making me, create this matrix. So if there was a
Sounds
way,
like a feature.
What's that?
That sounds good.
Yeah,
You're commenting your code.
So that's yeah, it's good, but it just takes a lot of time, I guess, as I'm going through each step. So maybe after the fact.
I don't know. It sounds like exactly what you're thinking about it. You're commenting.
I guess maybe after the fact, have something that kind of outlines what each does.
Maybe once you submit your lab, then we give you like commented.
Like a
reveal the hidden link.
Pro version of it.
Pro version. Okay. Yeah, that's not a bad idea. That's not a bad idea. Okay. Yeah, right here.
I don't know if this is like a comprehensive solution, but maybe even in the comments of the YouTube video, if you like annotated different times that you talked about different things, just to help us like.
Yeah, or like bookmarks or chapters.
Yeah,
or something.
bookmarks, or even like.
Yeah, that's a good idea. So
or say like at minute 5, I talk about this PyTorch documentation and I have a link.
Oh yeah.
Just so it's like easier to index into the information. Maybe.
That's not a bad idea. I like that. TAs make it so. Okay, last one. Go ahead.
Do we have to show overfit in the lab? In the video, it talks about overfit.
Yep.
And the grade breakdown. It doesn't
Yep.
mention overfit.
Well, that's in the deliverable part it does. Oh, I see what you're saying. You're saying if you just type in the code, it doesn't overfit, and then in the percentages, you're saying.
In the lab spec, it says top 3 show overfit. But
Yes.
in the actual grade breakdown, it doesn't say anything about doing overfit.
We would like you to show overfitting. So I'm sorry that was unclear. I'll revise that. Okay, go ahead, quickly.
And then with the overfit, with that in mind, do you actually want to show that the validation set like really gets a lot worse? Or
Ideally.
Just worse. Because mine is worse for like say parallel.
Yeah. So
The model is too simple. So the model that we used in that lab is too simple to actually show like dramatic overfitting. That's why if you were to use a batch size greater than or a data set size any greater than your batch size, then you'll get noise and the validation will be inside of that noise. That's just because the model is too simple and it's hard to overfit. So you can get a gap, but really one of the only ways to get a clear gap is to set the data set size equal to your batch size so that you're always training on the same batch every single time. And you can get overfitting there, but otherwise there's some noise and the noise hides the validation gap. So it's not going to be that clear, but you
Yeah.
should still be able to get the two lines and have there be a gap. The gap just won't be enormous. In later labs, it will be bigger, or can be bigger.
By the way, I know we haven't really talked about overfitting yet in class. We'll talk more about it for those of you that are wondering what's going on. But the short answer for this lab is, if you're not careful, your model just memorizes your training data. It doesn't learn how to generalize. So it does really well in your training data, but then when you test it on new data that it hasn't seen before and hasn't memorized, it does really badly. And that's the effect we're looking for. So the way to do that is just to shrink your data set super small so that it essentially memorizes just a couple data points. Then we tried out something new, just to give you some random answer. Okay? Good. I'd like to move on. If you have any other questions about the lab or any discussion, talk to me offline or on Piazza, and we'll get going with the lecture. Unless there's other burning questions or comments.
How long did it take them?
Oh, for those of you that finished lab 2, how long did it take you, roughly? Just shout out some numbers.
An hour and 7 minutes.
All 3 parts? Multitasking? What, 3 hours?
3 hours.
3.5? Okay, good. That's about what we're like. Okay, great. So last time we talked about loss functions, we talked about regularization, we talked about softmax versus thin loss. So today we are going to talk about computation graphs, and we're going to try to get to derivatives and gradients, and the chain rule of derivatives, and automatic differentiation. So that's a lot to cover in one lecture. I don't think we'll quite get there, but we'll see how much progress we can make. So just so you know, I'd like to illustrate just a little bit where we're going in the next couple of lectures. So here's like a little diagram about modern machine learning. You take the idea of a computation graph, which I'm about to explain to you, and you take the idea of automatic differentiation, which I'm also about to explain to you, and you combine it together and you get something called a gradient. And it's really, really easy for you. And then you combine it with an optimization algorithm that lets you use those gradients to optimize the loss function. And that gives you modern deep neural nets. And all of this stuff here is what PyTorch is doing for you. So PyTorch is a framework that helps us do all of this stuff really, really easily. That's why we're teaching it to you. But I don't want to just give you the tool without you understanding what it's doing. That's the purpose of these lectures. So we're going to cover all these different parts. Okay, but I'd like to do a brief interlude. So far in this class, we've only talked about one layer neural nets. Very simple, linear things where, like this, where scores of, say, some image classification problem are just a linear function of the input. And you could represent that this way. You have an input layer with a bunch of neurons, you have a bunch of connections represented by the weight matrix, and that gives you some output. Okay, but I'd like to go through a little hypothetical exercise with you now. So suppose a bright and enterprising student comes up to me, and comes up to you actually, comes up to you and says, you know, I've been thinking about Dr. Wingate's excellent deep learning class. It's fantastic. But I was thinking about this idea that one layer neural net, and he said that if we use multiple layers, it gives us more powerful function approximator, more parameters. And so this student says to you, so I've been thinking, you know, I saw a picture like this, where you have the input, but then you have another layer, like a hidden layer, and then the output. This seems like this would be more powerful. So he sketches up some equations and says, all right, here's my new model. I'm going to let x be my input image, and I'm going to multiply it by a weight matrix. That's going to give me my hidden layer. And then I'm going to take my hidden layer and multiply it by a weight matrix, and that's going to give me my output. And you look at your student friend, and what would you tell them? So I want you to talk to your neighbors, and I want you to discuss this for just a second, okay? And then I want you to tell me why this idea would work or not work, okay? 30 seconds, go. Talk to your neighbors. Figure this out.
So, as far as I can tell, let's see, S is the output, right? And so you're just doing the same thing twice. So you have to have two different sets of weights, so it'll take more time to have a represent more. But like other than that, it'll be more. It'll have more complexity that it can handle.
How did that machine learning course
That's true. You can't really know.
All right, what do we got? So who thinks that clearly, since this network is twice as deep as our original network, it will be twice as powerful? Anyone? Okay, okay, good. So was this going to work? Yes or no?
Yeah, it works.
Will it work? Okay, who thinks it'll work? What do I mean by work? Will it work better than the original network? Will it give you any additional expressive power? Now hold on, you have more parameters, right?
No, we don't.
Okay, so I saw some people shaking their heads. So what's going on here?
So
Go ahead.
it collapses, it basically just collapses back and down into W times X because there's no nonlinearity in it.
Okay, so I think what you're saying is this. If we go ahead and substitute H for what H is equal to, then we see that the output layer is a matrix times the input. But you're saying,
Basically, after you've done that computation, it's no more powerful because of no.
okay, you're struggling for words.
Yeah.
Give us some words, Jane.
Just set your big W equal to your W1, W2.
Okay. So you're saying, so if S is W1 times W2 times X, and you're saying, well, okay, so linear algebra is associative, right? So we might think that we do this calculation first, and then we do this calculation. But actually, we can do this bit first. And you're saying if I just multiply these two wave matrices together, that just gives me another matrix. And that is essentially the same as this. So, and it doesn't matter how many layers we do if we do this. We can have 100 layers, and we get no more representational advantage, no more power than if we just had a single linear layer. Or another way of saying this is what my graduate advisor once said to me. He said, linear of linear is still linear. Okay, so just adding more linear layers to an already linear function approximator doesn't help us at all. So,
See, I'd actually say it even worse than that because not only are you not gaining anything, you're doubling your parameters.
oh yeah, right. So
You're
it's almost
essentially
like
just convoluting the problem
you're making it harder.
and making it harder for, again, your loss function to actually find what the real parameters
Yeah,
should be.
maybe. Sometimes it's actually good to have lots of different ways to get to an objective. Sometimes over-parameterization is a feature, not a bug. But you're right. Certainly these are unnecessary from a representational standpoint. Okay, so what do? So in normal machine learning, normal deep neural nets, we have to add some sort of nonlinearity. So before we had this linear score function, but you can imagine creating a 2-layer neural network, and as long as you have something here, we'll call it G for now, just some nonlinear function, then you eliminate the possibility of that linear collapse. And so this is the form, the mathematical form, of all modern deep neural nets. Something like this, where you have a linear bit, possibly plus a bias, goes through some nonlinear function. The nonlinear function will typically operate element-wise on each element of the vector, and then maybe go through some more linear stuff. And then it's really easy to see how you can extend this to very deep neural nets. Linear, nonlinear, linear, nonlinear, linear, nonlinear. Just keep going. So, and now these parameters, now you get lots of parameters, and whether or not they're redundant, we don't know. But the point is now we have something that the deeper it gets, the more powerful it gets, typically. Okay, and this little g is called an activation function. And so throughout this class, we're going to talk about different activation functions and their properties. By the way, this is, if you remember this figure from the first day of class, now we have the tools to understand every bit of this little diagram, artificial neuron. So you have inputs x get multiplied by weights. They're summed up via dot products or matrix vector multiplies. You go through some activation function, which is these little g's, and you get some output. Okay, and here's some common activation functions that we'll study. So we won't go through a lot of these in detail, but there's a couple that are really important, either historically or practically. So sigmoid is one such function. So sigmoids were the original nonlinearity in neural nets. So the sigmoid function here, often denoted, this is sigma of x and sigmoid. It's a squashing function. So 1/1 plus e to the negative x. So when x is really, really big, this essentially goes to 0 and you get 1. When x is really, really small, this goes to 1, so you get 0. So the output of this function is always between 0 and 1. And people loved this idea. They thought, oh man, sigmoid, that's awesome because it's like neuro. And what they meant by that was the brain, if you think of any neuron in the brain, it actually is electrical, but it's electrical in a very specific way. It has a firing rate. So little neurons sit there and they fire at a certain rate. And when they're really, really excited, they fire faster, and when they're sad, they fire slower. And so the people thought, oh, sigmoid is great because there's natural limitations to the brain. You can't fire any slower than 0, and you can't fire any faster than some upper bound. And so the fact that this is bounded, that feels neurologically plausible. Turns out this is a huge mistake. This is like one of the great missteps of modern machine learning, was to use this function. Oh, it also has like this beautiful derivative. Just like the math works out so elegantly. So everyone just loved this thing. But it was terrible for various reasons that we'll talk about in just a couple lectures. The other options, tan, this is the hyperbolic tangent. It's very similar to the sigmoid, except instead of going from 0 to 1, it goes from -1 to 1. This is the modern, this is like the state-of-the-art function that most people use right now. It's called the rectified linear unit. And it's about the simplest possible nonlinear function that you could imagine. So it's literally a piecewise linear function, which piecewise linear is still nonlinear. And it's got two pieces, a 0 piece here, and then an identity piece there. It's like, if you had to come up with a really dumb nonlinear function, this is it. But it turns out this is sufficient. Like, this is sufficiently nonlinear to power most of modern deep learning. And it has some beautiful properties as well, which we'll talk about. A couple of others, there's the leaky ReLU, which just takes that little 0 bit. The big disadvantage of the ReLU is that the gradients over here are 0, because it's flat. So if you make it leaky, you just put a little bit of a slope on this part, and then there's a gradient that tells you where to move. Max out and the LU. So, and then there's tons of others. So it's a very active area of research is which activation functions matter. Okay, so this is the shape of the neural net. Inputs come in, they go through weight matrices, they go through one of these things. By the way, these things operate element-wise. So if you give me if I say sigmoid of x, where x is a vector, what I mean by that is apply the sigmoid to each entry of the vector. Okay, good. Any questions? Oh, yeah, good.
Is the leaky ReLU better than ReLU for what we know now, or do most people just stick with ReLU, or just it depends?
So it's so better is very, very difficult to either prove or quantify. There have been papers written on this, but they try to benchmark these and see which is better. The ReLU has several advantages, one of which is super easy to implement, and like on the GPU. So it's just a couple of instructions on the GPU, and very, very easy to calculate the gradients because it's either 0 or the identity. So it's got a lot of nice properties. So computationally very efficient. Does it work better? Like, do other things work better? Like, there's no other activation function that is so clearly dominant that I know of. I mean, if there was, I'd be teaching you that function. So my sense is that the overall topology of the neural net matters much more than the choice of activation functions. Like how many layers you have, how they're wired together, whether or not you have skip connections, that sort of thing matters more than this.
Okay.
I don't know if my TAs disagree. No. Okay, good. All right, so then let's keep going. Enough about activation functions. Now I'd like to tell you about computation graphs. So this is a key idea, very important. So I want you to pay attention. And if you weren't paying attention, then pay attention. Okay, so here's the idea. Computation graph is like a parse tree for a mathematical expression. Okay, and it's a very simple idea. We don't need to get hung up in any details here. Let's imagine that I have this little calculation up here. I have my little function, which is a linear function of some inputs. I have my loss function, which is like maybe the hinge loss thing. The idea of the computation graph is it's just a little graph that shows all the dependencies between the elements of this calculation. So for example, here you have x, and x and w both feed into a multiply, and that gives us an s, and that goes into some hinge loss thing, and that gives us an output L. Okay, so very simple idea. If we were to expand this function, okay, sorry. So now I'd like you to talk to your neighbors, and I want you to noodle on this. So now you know about computation graphs. That was it, literally, like that's all it is. I would like you to diagram the computation graph for this. So don't get scared. And so, sorry, here's the rules of what I want you to do. Take a look at this expression, and just try to diagram it at the same level of complexity that I just showed you. So don't like do n pluses, do 1. And you sort of show me the coarse dependencies between x's and f's, w's, lambdas, and r's. Does that make sense? So when you're done, your diagram is not going to look much more difficult, not much more complicated than this. In fact, it'll look almost identical. Does that make sense? So keep it high level. Okay, so give it a whack. Go ahead. Go try to sketch out what does the computation graph look like for this. We'll take 1 minute on this. Go ahead, you can work with your neighbors. Go ahead and chat about it, see if you can figure it out. Get it?
I didn't even get it.
Lost.
No. Competition graph is basically just a way it's a pressure.
What does hinge loss represent?
That outside. Okay. And so you're just basically breaking it apart. So we have an f function that is taking a negative x, and then you're just subtracting those, and then you're calculating lambda. Okay, so within the innermost sum. Okay, so whenever you're incorrect, so essentially when j is equal to yi, so you've got the wrong label, you take the maximum of either 0 or this function minus the same function. So the function
Alright, what do you got?
What?
Who's got it? Who's willing to tell me what to do?
Oh, the difference.
What is,
The maximum.
who's got an idea? Yeah, go ahead.
You want me to like sketch out the tree or whatever?
Here. Well, is it simple enough that I can draw it? You just like air sketch it? Okay, go ahead.
So obviously the top node of our tree is the entire point, so L. And then first we have a multiply between 1 over n.
Okay.
Assuming n is a variable, I don't know.
Okay, n is a variable.
Yep.
Yep.
I don't know if you include that or not.
Yep.
And then that big section is the big summation.
Okay.
Whatever that might be. And the summation, I don't know a good way to abstract this, but essentially, right, it's a summation between lots of different elements that all have the identically same parse tree underneath them.
Okay.
So you can probably just say one of them, and then we just know it's.
You're saying we've got a bunch of these things, and
Yeah,
they're all
it's a
feeding
bunch of
in
those
some
things.
sort of plus node.
Yeah.
Okay.
Yeah, each of those have their own parse tree, but it all looks identical.
Okay, and what do these depend on?
So those depend on, so we do double summation, but you,
Okay.
you just wrap it all into one big one, I guess. So they depend on an addition between our hinge loss and our regularization term.
Okay, wait, so hold on. So, sorry. Each of these boxes, what does it depend on?
Each of these boxes.
Depends on x?
A max.
Okay, well, there's a max. Yeah, inside of it, there's a max.
X and W.
Okay, x and w, I heard. So there's an x and a w, like there was before. So each of these depends on an x? Depends on our input? Is that right? And they also depend on w's? And then you said something about.
On functions of x and w, not x and w.
But that's what the boxes are functions.
Oh, no, I think the boxes are max.
They depend on f of x and w, not x and w.
Yeah.
Okay, so there's like inside of here, there's maybe some f of x,
Yeah.
and there's a max, and something like that.
Yeah.
Okay. Keep going.
Wait, I'm lost in now on what you're representing, so.
Okay, so let me tell. Well, okay, go ahead.
Is it possible to represent this without thinking about the summations? do it.
Yeah, that's what I wanted to do.
So what we would start, the inputs would be like 0, X, W, 1, and lambda.
Yeah, so somewhere there's going to be a lambda. That's going to be an input.
That'll be, for later, right?
Yep.
But then you have to pass X and W into your function. I don't know exactly how. I'm a little confused about this difference between the J and the Y spot.
Okay. It appears that I have confused you. So let's back up. I'll just tell you what I was thinking. Okay. This is what I have. This is all I wanted. Sorry if that was unclear. Sounds like it was. Note to self, we'll improve this part for next year. So the idea is, what I'm trying to show is course dependencies. It looks like I actually forgot the lambda on here. But so the idea is you have x's and w's. They're feeding into a multiply here, which is giving us f's. And that's giving us scores, which are going into this Hin's loss function. But then this whole bit is being added to this R function, which only depends on W. So W is flowing two different paths through this computation graph. And at the end, they get summed together, and that gives us our final output loss. Okay. So it sounds like none of you would have gotten that from my very brief explanation. Go ahead.
Yes, basically you just switched all this like summation stuff.
Yes, I switched all of that into Hin's loss. Yeah, sorry. I probably should have made this a little bit more abstract. Okay. Good. Well, we're all learning. So, okay. So the idea. Oh yeah. Sorry. Go ahead.
So talk about the Hin's loss. What's that?
Well, we talked about that last time. Were you not here?
No, I was here.
Okay.
No, I'm sorry. I was just wondering, is that represented in the equation that there's a term max?
Yeah. So remember the Hin's loss. The Hin's loss was this little bit where we sum over everything except that that's not the right answer. This max, and this I think we called S sub j, and this was S sub y sub I. Good. Okay. Sorry if that was confusing. Okay, we'll try again. So I was going to have you do this, but now I think I'll just talk through it. So the idea of computation graphs, I think, are very powerful and very intuitive, despite my flawed presentation of them. So here's a paper, and this is a paper called Skip Thought Vectors. It's from a couple of years ago, and right here, 1, 2, 3, 4, you see these equations. So what I was going to have you do for your next little exercise was this, we're not going to do it. I'm just going to talk through it. And what I wanted to point out was you have no idea what any of these letters or symbols means, and yet you could probably diagram the computation graph for it. You would know, for example, you're like, okay, well there's this thing called RT, and RT depends on a W, and it depends on an XT, and a U, and an HT minus 1. And there's a ZT, and a ZT depends on the XT, and the W, and the HT, and the HT depends on these things, and this HT depends on these things, and you can sort of sketch it all out. And that's all I wanted you to think about was how things depend on each other. Okay, so that's the idea of computation graph. Now the reason this is significant for deep learning is because we'll be using it to help us calculate derivatives efficiently. By the way, these things can be very, very complicated. So here's one. This is the computation graph for something called the neural Turing machine, which is a deep neural net that actually is like a Turing, learns to behave like a Turing machine. So they get really, really complicated really quickly. Luckily, you don't have to manage most of that complexity. Things like PyTorch will build the computation graph for you, and then we'll use that in various ways. Okay, so how do we use these? Sorry, are there any questions about computation graphs before we move on? Yeah, go ahead.
Why would we use computation graphs? Would it be like so we can know
okay, yeah.
what like dependencies are, so you can like
yes.
variables and know beforehand?
Yes. So the idea of the computation graph is once you sort of know how everything is being, what depends on what, you can do several things. So one thing you can do is sequence your operations. So you can build a computation graph in memory without actually doing the computations, and then you can, for example, compile it, or look for optimizations, or look for chances to share or reuse sub-quantities. Or, in our case, we'll analyze the computation graph to calculate derivatives automatically. That's what automatic differentiation is. Good question. Good. Any other questions before we move on? Okay, so like I said, it's like a parse tree for source code, so it's like the parse tree for a mathematical expression. Okay, so I keep saying stuff about gradients and derivatives and automatic differentiation. So this is the last little bit of deep neural nets that I want to talk about. So do you all know what gradients are? So who's heard of gradients? Most of you, all of you, okay. Anyone not heard of gradients? Okay, great, you've all heard of it. So the idea of a gradient is just a vector of partial derivatives of a function. So I think we'll skip the visualization in the interest of time. But here's the idea. We're going to frame learning as an optimization problem. And the idea is that we'll have some parameters, things like linear weights. And we'll have some score function, say linear. And we'll have some loss function, say one of these. And that'll give us some computation graph that looks kind of like this. We'll have W's, which are weights, things we can tune. We have data. They'll go through scoring and loss functions, and eventually at the end, we'll just get a single number out. That's the loss. And what we'd like to do is adjust the W's so that that loss number goes smaller and smaller and smaller. So how do we do that? How do we optimize the loss function? And the strategy of essentially all modern deep learning is calculate the gradient and follow the slope. So who has ever used gradient-based optimization before? Okay, so far fewer of you. So here's kind of the idea. So let's suppose that, actually let me show you this little video first. So just so we're all clear, I have this little video here just to help us out. I have this little video here. So this is just showing, so remember that the derivative of a function is just the slope of that function at any point. And you can always think of the derivative as the direction that points uphill. So the negative derivative always points downhill. And that's a great thing because we'll want, when we optimize our loss functions, we'll always want to make it smaller. So the derivative will tell us, well, here's one direction you could go, and if you moved your parameters in that direction, the loss would get just a little bit smaller. So let me see. So this is showing some random function, x to the fourth over 4. And this is showing what happens to the derivative as I move x around. And you can see that this always follows, well, this is the slope of the function at any point. And so here's a same sort of thing except in 2 dimensions. So now imagine that we have a function of just 2 weights, W1 and W2. And color here represents the value of the loss function. So you can imagine that the loss function maybe looks like a bowl. Start off maybe here. This is your random initial guess of the weights. And what you'd like to do is move around on this surface and try to go lower and lower and lower and lower and lower. And so the minimum of this function is, would be right about there in the middle. So does this visualization make sense to you? We're going to show some more of these in just a second. Go ahead.
So isn't that 3 dimensions then?
Isn't it 3 dimensions? Yeah, you're thinking like, hey, the bowl pops out into the 3rd dimension. Sort of. So we have a 2-dimensional parameter space we get to skate around in. The 3rd dimension is the value of the loss. So it's not something that we get to fiddle with directly. We can only fiddle with the loss indirectly by fiddling with the parameters. Does that make sense? Mostly. So it is like the loss is it's kind of like an extra dimension to the graph. You're right though, we could plot this as a 3-dimensional object and it would look like a surface, like a bowl in 3 dimensions. Okay, good. Ask more questions. I saw another hand. Go ahead.
Is there a way of visualizing higher dimensional gradients?
Actually, there is there's a really funny quote by this guy named Jeff Hinton, who's like one of the fathers of modern deep learning. He says, to visualize things in, I think he said like a 30-dimensional space, just visualize it in 3 dimensions and say to yourself, 30 dimensions, 30 dimensions, 30 dimensions. So I mean, the answer is no. We're not good at that. He says everybody does it. I don't do that. So I think there's no good way to visualize these things. You can visualize various statistics and projections and things like that, but yeah, this is one of those situations where visualizations are great for low-dimensional things. But you just kind of trust the higher dimensional generalization through the math. But, yeah, go ahead.
Just one comment on that. You can visualize 2 at a time and then choose 2 different ones, but as soon as you change one of them, you're changing the others. And so you can't truly, but you can get little snapshots of it if it's helpful. Right?
Yeah, so it is tricky. Now, just to be absolutely clear, I'm showing this little example here in 2 dimensions, but remember when we talked about even the very simple linear classifier that we've been going through, we already had 30,000 parameters. So this surface would exist in a 30,000 dimensional space, plus 1 for the loss. And the idea is we want to know which direction should we go to make things smaller. And that's where the gradients are super, super helpful. Okay. So this is a stylized machine learning algorithm. Okay, this is kind of the way it works. The idea is, this is called gradient descent. And the idea is we take our loss function, we take our data and our current weight setting, and we evaluate the gradient. Somehow we calculate the gradient. That gives us the gradient of the weights. So remember, this is a vector. It will be the same shape as the original weights, and so we can just add them together. And so the gradient says, hey, if you go in that direction, that's downhill. So we'll take a step in that direction, and then we'll recalculate the gradient. It says go that way, go that way. Recalculate the gradient, say go that way. We'll keep doing this over and over and over again until we reach some convergence criterion. And so we can literally just add the gradient to the weights at each time step. Now, we'll see that this is actually a pretty bad idea. It works, kind of, but we can do much, much better than this. Go ahead.
So this assumes that we know the loss function.
Yes.
I'm trying to think of like real world examples where we would know the loss function in advance and need to run this. I'm just having a hard time like making this a practical example of a practical problem.
Yeah, so we always know the loss function. You're exactly right. That's just part of the design of the learning problem. So we set up the learning problem and we say, okay, here's our data. And we have this bucket of models that we've parameterized with something like weights. And we want to adjust those weights to figure out what the best possible model is. And the loss function is the thing that's going to tell us how well we're doing. And so designing the loss function is a critical part of sort of formulating this, because the loss function tells us what it is that we care about.
Okay, I see. Yeah.
So for example, in classification, if we have an image input and we want a label out, we have to somehow tell the learning algorithm what happens if you get it wrong, or what does right even mean, or what if you're mostly right, those sorts of things.
That makes sense.
Okay, yeah, thanks.
Is the step size the lambda in that earlier equation we saw, or either in relation?
Step size is typically alpha. It's not related to the regularization lambda at all, no. Step size is just something that tells you how big of a step you want to take.
Okay.
And it's a hyperparameter that you have to pick somehow. And there's tons of literature about how to pick it, and it's really hard. And actually what we'll do is we'll use algorithms that pick it automatically for us. Go ahead.
So gradient descent, it'll find, it's guaranteed to find your common, right?
Yes.
Your absolute minimum. Sure you're going to find an optimal solution, or some optimal solution. But is there any way to find out, like, if there's a better one aside from just randomizing your input weights and trying again?
No. So, yeah, TLDR, no. The longer answer is, unless you make very strong assumptions about the shape of the space, what you're describing is the difference between local minima and global minima, and global optimization is essentially impossible in all but the simplest possible case.
Yeah.
So, yeah, no. And so that's a great unsolved problem in deep learning, is how can we come up with super powerful models that are crazy nonlinear and like super high dimensional and still say something about the quality of the solution that we come up with. And it turns out you can say a couple of things. For example, just preview, spoiler alert, it turns out local minima essentially aren't a problem. And the reason is these spaces are so huge that in order to be a true local minima, there have to be 30,000 dimensions that you can't move in, any of them. Like, that's just super unlikely. And so you almost never run into an actual local minimum. Plateaus turn out to be much more of a problem. We'll talk about that later. Okay, so how do we compute the gradient? So we've established this idea that a gradient is a very powerful thing. You're in some crazy 30-dimensional space or some 10 million or billion dimensional space when we have neural nets have a billion parameters. Which direction should we adjust all of those things to make our loss a little bit smaller so we're a little bit happier with the result? Well, we'd like to use the gradient. Well, how do we compute the gradient? So we only got 10 minutes. I was going to take you through numerical differentiation, which I think is useful, but we're going to do it really briefly. Okay, so has anybody ever heard of numerical differentiation? I'd love to hear. Okay, a couple of you, but not very many. So the idea of numerical differentiation is to rely on the definition of a derivative. So let's see if we can do this. So let's imagine we have some function of x, and this function takes an x as input and just gives us some number back out. And I would like to calculate the gradient, just the derivative of this function. So hopefully you guys all remember the definition of the derivative. So the derivative with respect to x of f of x is the limit as epsilon. Correct me if I get this wrong. I think I'm going to get it right. X plus epsilon minus f of x divided by 2 epsilon. Is that right?
Just epsilon.
Just epsilon. Okay, right. There we go. Okay? And so this is literally like the calculus version of slope equals rise over run. So we have some function. We want to calculate the derivative at f of x, which is tangent line. And so we're going to approximate that with a little triangle. And there's going to have an epsilon run. And this is going to be f at x plus epsilon. And this is f at x. So the difference is the rise. Epsilon is the run. Slope is rise over run. The derivative, the definition of the derivative is what happens as epsilon gets essentially 0. The limit as it goes to 0. Okay, so, but notice the key thing. You can approximate the derivative by calculating your function. So forget about the limit for just a second. Take your function, take an x, add epsilon, and then just subtract f at x and divide by epsilon, and that will be an approximation to the derivative. And that's the idea of numeric differentiation. So let's imagine we have some function, and we have some weight vector, and we'd like to know what's the gradient of this. Well, remember the gradient is just a vector of partial derivatives. So what we do is we take each one of these and we just tweak it a little bit. So we take 0.34, we just add an itty bitty bit of the number, we leave everything else the same, and we recalculate the value of the function, which in this case is our loss. So if it was 1.25347 here, we tweak that number, we get 1.25322 here. We subtract those, divide by epsilon, and that gives us negative 2.5. So that is the first entry in gradient of our function with respect to w. And then we can just do that for each of these parameters. So keep doing this. Okay, so talk to me. What is the problem with this? Oh, yes.
So these derivatives are of the, so I tend to think of it as like derivatives in my search space. Is that what this is? Are these all the parameters in my search space that we're taking derivatives?
Yes. So W is the space we're searching over. These are the weight matrix. And we'd like to know what is the gradient of the loss with respect to each individual entry in the weight matrix.
Before we said it was like the eigencat would be one column of W.
Yes, but how do we get there? So I'm sorry if I've jumped ahead, but when we first begin the learning problem, we have to guess at a W. And then over time, it will converge. In this case, it would converge to the eigencat. But more generically, we start off with some random W, and then we just need to know where should I go to get to decrease my loss. Okay, so what's the problem with this? Go ahead.
Super slow.
Super slow. Agonizingly, painfully slow. Why?
Because, I mean, we have 30,000 weights, and then we're computing the function twice for every single one.
So if you have a billion dimensional space,
I mean, I guess you could compute that.
you calculate a billion times to calculate the gradient, and then just take one step. And then you have to do another billion calculations and take one step. Okay, this is a terrible idea. Okay, nobody ever does this. So yes, that is the problem. Problem is that it's essentially impossible. So you might think like, oh man, well, so how are we going to get a billion-dimensional gradient? Like, that sounds impossible. But what's cool is nothing's impossible. The word itself says I'm possible. Okay, so how? How do you calculate gradients efficiently? And the answer is calculus. So, okay, so the idea is this thing called automatic differentiation. So automatic differentiation, I've said this a couple of times, but here's the idea. You give me a chunk of code. I use all of those identities of derivatives that you learned and forgot in high school calculus. So those tables in the back that says the derivative of e to the x is e to the x derivative of log. Those are systematic enough that I can actually write a computer program that looks at a program, goes through and finds all the mathematical operations, figures out what their derivatives are, and generates a new computer program that calculates the derivatives for you. And it is efficient enough that you can calculate all of the derivatives that you want, in other words, the entire gradient, for essentially the cost of one numeric evaluation. So it is essentially as fast to calculate the gradient as it is to just calculate the loss function. I have this little video here that's kind of a fun little example. So on the left, and this is very generic. So on the left is some, this is not machine learning code. This is a fluid dynamics simulation. And so what this video is going to show you is it's going to show you taking the fluid dynamics simulation and perturbing the initial conditions such that when you run the fluid dynamics forward, you end up in a specific final configuration. Yeah, pretty nice. So it uses the idea of automatic differentiation and gradients to be able to back out. Okay, so take the gradient essentially of the fluid dynamics and ask, what if I give you exactly the right initial conditions, and then I run the fluid dynamics forward, I end up with BYU. Okay, and this is because of the chain rule of derivatives. So we only have like 1 minute left, so I'm going to skip a couple of the visualizations here. And I think we'll just start here. So you guys hopefully remember this, but the chain rule of derivatives says that if I have some function and I want to calculate its gradient with respect to x, and there's some intermediate function q, then the gradient of f as it changes with x is the product of f of q and q of x. And I like to think of this as, well, how does f change as x changes? And then if there's this intermediate thing q, you can have